I think intuition definitely comes up more often in science than in math. In science, your goal is to find something useful. In math, you want to find something that is true. So it comes as intuition comes up more often in science. The question you asked is about the difference between and the relation between competence and pragmatism. I think there's a balance to it. Fundamentally, these two concepts are different. As the current understanding of how people do science, or there's a not newish field of science. The current understanding is that we would like to think people who do researchers, as having a intrinsic quality as how good they are. We can understand that as competence, and there is other things. For example, performance as of how many papers you produce and things like that. But again, there are definitely more than two things. For example, how external things affect you. I think there are many external things that can affect your career, and you do need to consider that. So you need to consider being pragmatic in a sense, but also keep it to yourself. Try to produce things you value most. For example, high quality research. You need to find different people take different position on these two topics, but I think you need to find your own balance. The reason why people need to be pragmatic is that to survive in the current academia, you need to be able to make a name for yourself and also get money so you can hire more students and things like that. And then you get to produce more papers and do more important research. But you cannot get lost into it and just to chase the fame or chase the money. And instead, you don't really do much of the fundamental field-changing research. So I think it's the question to everybody who do research, that's how pragmatic and do so-called pure, like before, like in the earliest sense, how to be a good researcher.
Hey everyone, I'm going to start today's conversation with a little PSA on Gaussian processes. Now, I know a lot of people when they're trying to get into Gaussian processes, they're immediately shuffled towards the great book by Rasmussen Williams called Gaussian Processes for Machine Learning. But I'm going to suggest something a little bit different. If you haven't actually started Gaussian processes, there are some better texts to be learning, in my opinion. And one of them is Mark Ebden's work on Gaussian processes, A Quick Introduction. I'll pop it up on the screen right now, and it shows you everything from like regression classification and then dimensionality reduction, which is very useful for building some of the intuition that we might want for Ruda's work, who's here today. You can also check out David Duvernod's doctoral thesis. I'll also pop that up. It's just a beautiful document, and those are great ways to get started understanding Gaussian processes. And then once you're sort of in the loop more, Rasmussen Williams is definitely the way to go. But anyway, for people trying to sort of hop on board with some of the more technical aspects of a conversation on Gaussian processes, I really would suggest this Mark Ebden work. It's a fantastic introduction. But with that, today's guest, we have Ruda Zhang from Duke University, and Ruda recently co-authored this really cool article on manifold learning and manifold regression using GPs. He did it with Simon Mack and David Dunson, who previously have been on the show. So obviously, a cool dude. But more importantly, Ruda actually has this like really sweet website. And so talking about like the intersection of math and science and things like that. And so obviously, I wanted to talk about that first. And also, basically, last night was pretty much until about midnight, I was having a man versus EC2 battle. So I wouldn't mind easing into these things a little bit more. So Ruda, welcome to the show. And yeah, we'll ease into things before let's talk about the intersection of science and math. Before we get into that, matrix variate Gaussians and Grassmann manifolds and all that. So you have this website. I'm going to pop it up here because people need to see this, and I'll have a link in the description below. But again, welcome to the show. And I'm just start popping in some of these great quotes that you have, because these are things that I want to talk about. Is that all right?
Yeah, well, thanks for having me, Glenn.
Yeah. Well, yeah, I was going through it, and it looked, you have this Wikipedia page where it seems like it's halfway between a blog and a wiki. And I really like some of the ideas, and I want to give this its dedicated time.
Well,
So,
let me talk a bit about my wiki first. So first, I do have a personal website. It's called Ruda.ct. And I started building my wiki before building my personal website, and there was much more content in the wiki. The goal of my wiki is just it's basically a place where I keep all my notes. So I have all these paper notes from undergrad, and just figure out if they're gonna just leave on the shelf, they probably will not be useful. So I have this huge project trying to digitize it into computers so I can search it. It's much more efficient. So then I figure, well, because all these basic knowledge are, for example, math, physics, and stuff are most fundamental. So why don't you just put it online and so everybody can use it? I mean, most of the use is intended for me to say, what is the definition of this, and then just search for it. Then I can just find when I have a freshest memory of that context. So that's the basic idea. But so that's the majority of the content on the wiki. But also, as Glenn noticed, I also have some more philosophical thinkings posted as articles on that. Yeah, so that's basically the structure of the wiki.
yeah, I was very pleasantly surprised when I started reading through, because I think the original reason I went through was because I usually just check out people's websites just to see if I can get more of an intuition on their research. And then when I came across this and saw some of the initial quotes, like, oh my, we need to have a separate conversation about these things. But yeah, so should we just hop in and start talking? Okay, cool. So I have his quotes right here. But he has this first quote says, mathematics. Sorry, I'll preface this with, I think this is heavily related to some of the things we've been talking about on the show previously about the interaction between inductive and deductive reasoning, sort of that formalized reasoning that's needed in mathematics and, for example, coding. And I'll just read the quote now because it's good. Mathematics makes your reasoning rigorous, but intuition makes you smart. Getting useful general results from a simple model is called smart. Mathematics provides universally correct answers, but never directly useful. Intuition and generalization help get extremely useful results, even though they're not always correct. And so, one, I think this. Do you think that this intuition aspect is really is undervalued in scientific researchers, where the value between mathematical rigor versus essentially intuition?
Um, I mean, it really depends on the researcher. I mean, the thing. I mean, this thing is like I wrote down a while ago while I was, during my PhD, and I think I thought about it when I was like trying to figure out what I'm gonna do for my academic career. So I have this thoughts, but I mean, as I do know more about how people do research, I figure it's a very complex subject. Say, I so is intuition undervalued? I mean, it may be, but it's not a blanket term. I think some people do value intuition in their research, but oftentimes it's not. You don't see that many research papers that just shows, hey, this is good intuition. There's something right to it. You don't really see that kind of papers often. They are rare if there are. Usually, what's the situation is many people do have smart ideas, like for example, good intuitions, but they would dress it up into technical terms so that it's more theoretically founded. Putting it, for example, you find a term that has somebody's name attached to it. It sounds much smarter than you actually say it out loud. What's the actual intuition behind it? So that's this dressing up of intuition make it less obvious. But I do think there are smart ideas out there. But this tendency tends to it says something about academic research because people tend to think intuitive ideas are less valuable than if it has a specific term or like named concept to it.
Yeah, definitely. It reminds me of and I've mentioned this several times before. There's this Radford Neal paper, and I think he's talking about slice sampling, and he just writes out his intuition on why it works, as in like why it has the required properties, like the Markov properties and things like that that you need. Um, but it's not somewhere he's saying like, oh, here's all these equations that make it work. He literally just writes in words for pages about why this makes sense. And I found that like it was a really refreshing thing because one, it was it's not like it was easy, but it was very helpful. And I definitely get what you're saying with the thing where people are saying like, okay, I have this intuition, but if I just say what the intuition is, it's not going to sound smart enough. Um, and well, obviously, like intelligence is a prized entity, especially in fields like ours where it's presumably required. And so, yeah, I guess I think there is that sort of social aspect where people are trying to dress things up. But I also saw in your work because basically in your papers you do try to describe the intuition behind what you're doing. In fact, even sometimes you say intuitively this or intuitively that. Um, is there is intuition? Do you think that there's any divide between, for example, like the more mathematical types of scientific research versus, for example, the more observational, less mathematically rigorous, where essentially you can get away with intuition more? Or do you think everyone tries to dress it up? Because I mean, I've read some sociology papers that take something that takes like one sentence to say and takes like a paragraph to make it obscure. What's your call?
Um, well, the thing about me is that I my research very interdisciplinary. I have seen research in very many different types of fields, from like the more formal, for example, mathematical and statistical research, to engineering and also economic research. Every field has its norm, and everybody. I mean, it happens that if they don't peek outside of their field, their research, they have a very specific idea of how paper should be written, which varies a lot across the different fields. Um, for I think in mathematical papers, especially in the more pure side of the math, the papers tends to be very just rigorous. Like you need to quote papers theorems, and then you prove theorems, and that's about it. You don't. There's no need to justify why this problem is important at all. And it seems like everybody should get it, even though it's not obvious at all. And then there is, for example, the engineering side of it. You many times you don't invent new methodologies for, like if there are new theories coming out from the side of mathematics or statistics, you just apply it and say, hey, it works in my problem, and that's a paper. So you don't have to invent anything. But as long as you say, hey, this is a shiny new method, and therefore we can write an application paper, and that's it. It can get published. So you only need to show that there's something methodological new, even though it's not yours. So it's the type of papers out there are vary a great deal. Um, so yeah, so this is my observation.
Yeah, cool. What sort of intuitions? Because you do write when your papers, at least the ones that I've read, you do try to give people a glimpse into the intuition. I don't feel as if you attempt to. Well, how about this? I think the work that you do is sufficiently complex, even for people with PhDs, that you don't need to make it sound any smarter or complex than it is. And so I think in your work you do try to provide that intuition. What are the types of ways that you try to provide that intuition? Because for example, I've seen where essentially you're talking about these alternative methods where they use essentially like uh, I'm not sure how deep we want to go into this, but like like tangential like tangents across a subspace. And it's like okay, well that sort of like twists and warps what the actual I will say loosely, the response function, or what the true underlying function is. So effectively, you're given this idea that, and you showed even visually how this worked, where effectively you have this thing, and you can see that these approximations sort of warp the intuition or warp the aspect. Is that how do you approach giving people intuition in your own work?
I mean, the GPS paper is actually very abstract and mathematical, and also it's going to a math outlet. But for every paper I write, I try to use a tone that is not so like cold and strict, but rather I try to explain things before I go into the technical stuff, so you can have an understanding before we actually go to the math. I think this is in general a good idea, and also uh, well, I mean, it's just a very minor thing about how I write my papers. I try to use first person tone so that it sounds more closer to the audience. But anyway, the well, for math papers, you have to be formal. Otherwise, it's not going to be published, because people just, I mean, you need to be rigorous. That's the bare minimum. But on the other hand, if you only talk about the formal symbols and how you prove things, then really people will take a hard time understanding it. The starting point of this, for example, the GPS paper, is how people can use it to speed up simulations. And for people for example, in science and mostly engineering, they don't really understand that. I mean, if you talk about manifold, people just shy away from it. But you want to have a better appeal to the audience. So at least you want your paper to be understandable to, I mean, in part to the audience. So that's how I see how I try to explain things.
Yeah, actually, it's funny when you say it's like, oh, I wrote these quotes down a long time ago. Because what you just said, you had this other quote says, which is pretty much mirroring what you said before. Mathematical proof comes after intuition. We need our good intuition to take us one step further than what is strictly stated by the models to broaden the results. Proof might be impossible, or at least drastically more technical. So it does seem, I definitely agree where you have to set the stage for what people have. And even in a lot of mathematical conjectures, people had this intuition that something was true long before they could prove it. And so this idea that I think that like mathematical proofs are simply being like etched out of the stone, where effectively they're just coming through these things by thinking purely deductively, and they just do math and they happen to come across things. That doesn't seem to me to be the actual psychological mechanism where people have an intuition about how the mathematics will work, and then they figure it out. And I think science is very similar, where people have this intuition about what the underlying phenomena are, and then they study and figure out if they're right.
Yeah, I think this. I think intuition definitely comes up more often in science than in math. In science, your goal is to find something useful. In math, you want to find something that is true. So intuition comes up more often in science. I mean, for example, one example I can give is when in my undergrad I studied mechanics. So one thing that is just being talked around the community is a concept called boundary layers. So the idea is that, I mean, fluid dynamics can be, I mean, it's tough. I mean, if you consider only the simple problems, for example, like fluid flowing in your water pipe, if the speed is really slow, you can describe it basically with a parabola, and that's really simple. But as soon as you get to something more complex, for example, you increase the speed, then you have the complex geometry, things get hard to study. So the concept of boundary layer is that it is proposed by a great fluid mechanic scientist, and so the idea is that so you have an object that is non-fluid, And then if you have, for example, incoming flow coming past it, then how do you study the flow around that? And so basically, if you have everything, previously this problem has been very difficult, but what he suggested is that, hey, the boundary layer is there, so there's flow far away from the object you want to study, which basically does not change much due to the geometry of this object. But there is a thin layer of fluid attached close to this object that separates what is away from the fluid field, away from it, and the fluid field close to it. There is so this separation of analysis makes the problem much more tractable. Even, I mean, when this paper was originally published in the early 20th century, the math is not there. They're just pure concept. And it is, I mean, it basically sounds so intuitive that people just say, this must be right. And then there are further research going on to show them, to provide a mathematical structure to it. And people actually found out that many things in the original paper was wrong, but the concept of boundary layer sticks. So that is, I think, an example of intuition helps the progression of the field.
Yeah, that is a really cool example. Hey folks, we're a few minutes into the show. This is usually the part where the podcaster talks about their sponsor or something. I'm not going to do that, but I will ask two things. One, if you could leave a like or a dislike based on your preference, and also let me know what you think about this topic, and also what topics you like discussed on future episodes of the show. That's it. Enjoy the episode. On that note, I guess you've sort of talked about this, like how intuition makes it possible to discover these truths, even if they aren't mathematically rigorous. Do you think that there is a different way that mathematicians think and dissect problems compared to empirical science? Because I mean, I'll say this, like I truly believe that like what mathematics says is true. Like, it is definitionally true. It is that deductive, undoubtedly true. And it's hard to think that could ever not be quite useful. But I guess the idea is, when you have these complex systems, it's very the reason mathematics is true is because it is so friggin' rigorous that it doesn't take missteps. And the problem is that the amount of complexity that you need to encompass, the world and those types of phenomena, like it's essentially beyond our capabilities to encapsulate so many of these important things with mathematics. So mathematics' great strength in the fact that we can believe it to be true is also a massive hurdle in order for it to be like empirically useful for many things.
Yeah. Well, the difference between mathematical thinking and scientific thinking, to me, is that being the great mathematician Ingrid DeVolchers in the Duke Math department, it has this course about applied math. It's called Intro to Applied Math. You will see in the syllabus that this course is about how useful math comes up in different fields of science and engineering. And there is a term that in that description that sticks to my mind is that watertight proof. That is, your logic has to be watertight. This is a required part of mathematical teaching, so which is not necessarily so in science. In science, I think it's more important that you find something useful instead of saying the logic is right. You don't start with thinking, is this logic correct? Oftentimes, the order is the opposite in science than in math. I think that's one of the main differences.
Yeah, and I like the idea of the watertight proof because basically one, it does there's only one type of logic that is truly watertight, and that is deductive reasoning. And what isn't watertight, and this something that bothered even David Hume came up with this, the problem of induction, where effectively observationally, there's no amount of observation that we can do that will fundamentally resolve ourselves from the problem of induction, where essentially observationally we have no guarantee that things will continue to act the same way that they do. So we'll never have a truly watertight scientific theory. Things can change. In
Yeah.
fact, some of our underlying scientific theories, literally like in the 19th century when they started digging up fossils. So essentially, we had this coming together of both geological knowledge and sort of that like the Darwinian evolutionary knowledge. And we had come up with this idea. It's like, okay, we're going to pretty much have to have this primary assumption that the universe will continue to work the way it does. And without that, we can't even do like the smallest type of science.
Yeah. What I'd like to add is that if you look at, say, for example, in college, I did my undergrad in big university, and we have a very strict. Even though I'm not my undergrad is not a math major, we are very strict about what math we teach, and we have very good teachers for math. For example, the mathematical analysis, basically calculus and more advanced type of it, is there are 3 books. Each of them is very small, very thin, but actually if you the teacher will tell you that don't judge the book by the volume of this. It's especially for math courses. It's a lot of work put into it, but they're just organized in such a way that everything is succinct and it's well ordered, so that it tricks you into thinking it is not so much. But that shows the characteristics of math is that there are a lot of work going into it, but when you present it, you organize it and you shrink it to the essence. But it's almost always the case, it's the after product of scientific or of a discovery. The ordering and reducing comes afterwards. So to me, there are many things. There are many useful concepts that comes up in the process, but when it comes into math, it's almost as an after product, and you present it in a way that's never what happened as it comes.
Yeah. Can I just ask you? So, what undergraduate course or degree were you pursuing first?
Well, it was called engineering mechanics. Well, it's basically mechanics. Well, according to the Chinese education followed the USSR system, which combines math with mechanics. Back then, mechanics is considered as part of applied math. So the good tradition of teaching mechanics, you need to have a very solid mathematical background. So yeah, that's the tradition.
Yeah, that's interesting because I can't help but think, in a lot of U.S. universities, for example, especially in the humanities, where they essentially say like, you're now out of high school, you're done learning math, and the only time you might have to do it is you have to take, I don't know, what are those called? The required like your variety courses or whatever. So since you get your liberal arts degree by you do mainly humanities, for example, and then you do like 2 science courses and you take a stats course and that's done. And I think that they're doing such a massive disservice to people by not having them continue their mathematical education and continue to build that intuition, because effectively this is a logical foundation, and the ability to sort of think about things in a mathematical um, context. Like, it doesn't matter whether or not you're doing um, something like physics and mechanics versus you're doing something like biomedical engineering versus something like, I don't know, zoology, which actually has plenty of math in it too when they're trying to figure out animal mechanics. But the idea is, there might be this concept that there's levels of math that you need to know to excel at a certain field. and that it sort of ends and peters out, has that exponential decay, and at some point it's effectively zero. It's like I think you're screwing people over in that. Like everyone needs to know math and think about these things because it fundamentally changes the way you think. It's like coding, where the process of formally going through and constructing code is to me very much the same way that you would formally go through and construct a logical argument. And that's why I was interested in what you're doing so effectively, trying to figure out what the bounds were on people thinking that you need a lot of math. Mechanics to those seems like a very obvious one. But yeah, actually, that brings me up to your next quote, which I thought was really fun. It's on abstract thinking. And you say, abstract thinking, i.e. manipulating vague concepts in the mind, helps one do rewarding research. This is because once concepts get well defined and problems clearly formulated, pioneering work must have been done. According to convexity of cost function, the remaining reward in this research area is limited, while the cost is prohibitively high. So again, I guess the reason that it reminded me of that is because obviously I think the mathematics that you're talking about that's what allows us to manipulate abstract concepts. So we abstract a way to get to the math, we can manipulate it in that space and move back down. But I wanted to hear about this convexity of the cost function. I like how you basically talk about abstract ideas and then you use an abstract mathematical idea to describe the abstraction itself, which was really funny. But what is this cost function, and why is it convex?
Well, so I mean, when I wrote this, I was deep into economics. So they use the concept of convexity and concavity a lot. So the idea, I mean, let me try to, let's not stick with the convexity or concavity too much, but it's just the underlying idea is very economical. In economics, it's called law of diminishing returns. It's one of the fundamental laws in economics. There aren't that many fundamental things in economics, but this is one of them, which basically says, I mean, I think one of the most basic foundations of economics is that people are rational. I mean, well, this is not always true, as the recent research are trying to argue, but in this case, the people are researchers. People who do research, we can reasonably assume that they are more rational than the others. But so applied to the scientific discovery, people tend to sort problems from easy and important to ones that are tough and more fringe. So you see, when people get into a field, there are many problems they can choose from, and they will sort things in this order so that the ranking of the reward will be from high to low. You will pick the highest reward first, and then goes into that order. So with
like a knapsack problem, it's like a knapsack optimization.
Yeah. So as long as people are rational, we do this type of sorting that creates the evolution of rewarding. I mean, marginal as is a concept that basically the gradual increments of the reward will decreases. So this is the diminishing, the law of diminishing returns, and if you so this is a monotonic function that goes down. If you integrate that, you would have a concave function. So that's your total reward. But anyway, the basic idea is that because people do this type of sorting, they pick the highest rewarding thing first. What comes next will always be less rewarding, or almost always less rewarding than what comes first, what has already been discovered. So yeah, that's what goes into that quote.
Yeah. So like, just to recap, because I think so the law of diminishing returns, I think it was probably pioneered by like Karl Menger, I suspect. So like I think he's like 19th century German economist, and that original law of diminishing returns is something around the idea that what's interesting about this concept, I think, is that it actually went hand in hand with people coming to realization that value is subjective in economics. So effectively, it's like 2 apples is not worth twice as much as one apple. And if you have a million apples, it's not a million times more valuable to that one individual. So they want it less and less. Similar to the idea that's like a diamond in the desert is not worth as much as a glass of water. Actually, in that case, I might be quoting lyrics from the Prince of Egypt musical, but yeah, and again, that the idea that yeah, no, the Prince of Egypt quotes like a lake of gold in the desert is worth less than a cool fresh spring or something like that. But again, the idea is that the value of these things change depending on what quantity and whatever your subjective needs are. And so here I like this diminishing returns thing because effectively is the idea that if you're extremely pioneering, you're going to get this very high rate of return. And then as more people jump on it, they're only going to be incrementally adding to it. And then the cost prohibition is the idea that, and that I'm asking you, is it the fact that we can't keep piling on more and more researchers because effectively it's costing more researchers and having less and less in return until eventually it's saturated?
Well, honestly, the two concepts in economics, one is cost, one is reward. Then it's really, you can consider them as mirroring each other. So the cost is the opposite of reward. So you can separate them, but you can also consider them as the same thing. So one thing is, as I explained, the reward of the problem itself. If we want to talk about the cost as a separate concept, then for example, it does pile up as for example the latecomers. Well, if they want to do some research, they need to read incrementally more papers than what people have come before them. So it has the time they need to spend to ever start research in that field is going to be increasing over time.
Oh yeah, that's a really good point. It's that the setup cost to make progress becomes higher and higher. It's sort of why effectively, in the like 18th century, someone could be extremely learned by having covered like a few books. And effectively, they pretty much know all there is in human knowledge or to catch up to it. And I think there's some prominent mathematician I heard who said the reason he started in topology it was combinatorics was because effectively you didn't have to do as much to get up to the cutting edge of the field because it was underdeveloped at the time. So that's a really interesting point. And just as a quick thing, since I know that that you think a lot about economics, when I originally read that quote about the idea that when the problems are well formulated and pioneering work must have been done, I was actually thinking about like efficiency frontiers, where effectively, if you have the frontier of scientific knowledge, that when people work within the frontier, which means they aren't really advancing it, that effectively the cost is that was sort of the cost that I was thinking. So it's sort of interesting that, and by the convexity of it, I was essentially thinking of it as like a convex efficiency frontier, and that it becomes harder and harder to find points outside of the efficiency frontier, which would then essentially mean like an increase in scientific knowledge.
Well, that will be a different concept. So, but if you're talking about the Pareto Front, then yes, it's. I mean, one thing, for example, the Pareto Front comes up is if you picture the space of problems, you put two axes onto it. One is the reward, the other is one is the difficulty of it, the other is how important it is. Then you have this natural Pareto front that the low hanging fruits will be on the bottom left, but then there are some so everything on the lower left of the Pareto front will probably have been already done, but what is left is, depending on the degree, the more or less more difficult and less important problems are left undone. So that would be the case where you have a front that is curve in a space of problems.
That is very cool. You mentioned latecomers, and you had this quote that says, more often latecomers cannot see the direction and intention which guided pioneers through the theoretic research. They are lost in the jungle of technicalities. So a minute ago, you're talking about effectively they have to have there's such a hurdle just to get involved. But is there more to it about getting lost in the technicalities, where they've lost the direction, they've lost the intention?
Well, as I mentioned earlier, latecomers has a latecomer disadvantage because there are so much more to catch up with. So it's unless it takes more time to see through what is going on. And I think there's another point to it is that latecomers, there's one tendency for people to do research, is to put two ideas together, basically do combinations. You can create a lot of things with combinations, and in an extent, they are novel, so potentially you can publish. But how important is that combination is a question that should be asked. So in many scenarios, such like combinations of things are maybe like technically interesting and methodologically new, but the use of it, because the combination happens so rarely, the use of it becomes much more fringe. So that's when people lose the importance of the questions they are asking.
Yeah, I was also wondering if this relates back to your previous thoughts on intuition, where effectively latecomers, because there's such a body of technical results at the time, so effectively they've got start at the beginning where you have essentially the intuition phase, and then the intuition phase gets ossified or becomes more technical, and so effectively then we have all these technical results, and so it's up at this peak. And then when a latecomer comes in, or we can just call it a newcomer, so it's a little bit less pejorative, but latecomer is just as good. That effectively they're presented with now they don't only have the intuition, but there's this great body of technical aspects that they need to come to terms with. And so effectively, it's a bit of a misdirection that instead of having them focus on the intuition and saying, build from that we're saying focus on the technical bits, which is essentially the end product. And so effectively, it's like people are looking at like the canned spam and not looking at, whatever's at the beginning of the production line. So it's effective. They're busy saying like focus on this end result, not, or maybe better saying you're focusing on the paint of the car, not how the car is made. And the problem is with scientists, you're supposed to be figuring out how the car is made. So it's a little bit of a misdirection. Do those sort of ideas tie in? The latecomers missing the intuition and focusing on the mathematical rigor instead, for example?
Yeah, I do agree with you.
Cool. So you had another cool quote here, which is about pragmatism, and this is something that I've been really looking forward to this question, because I've been wondering about too, and I'm looking forward to having someone to discuss this with. You say that pragmatic considerations of researchers / scientists / engineers include things like industrial need, competition, challenge problems, funding, publication, graduation, tenure, etc. Researchers who don't have pragmatic considerations often lack competence and get trapped. I think there's something to this where, what is the interplay between the pragmatism and competence? I always thought that like they both require critical reasoning and prioritization. But what do you think that interplay between pragmatism and competence is?
So the way science is done today is way different from what is done in, for example, when science started in, for example, the 18th and 19th centuries. Back then, you have a bunch of rich people or people who born into rich families. They do have everything they need, and if they happen to have the curiosity and the smartness to conduct some research, they just do it. And they don't need to consider about how to raise funds and apply for grants and to support themselves. Now it's very different. It's a profession where people who want to do discovery of knowledge, but they don't necessarily have the support that comes for granted. So this is where it comes
literally for granted. I like that. I like that play of words. Sorry. Go on, sorry, but you're clever on that one. I just had to call that out. So go on, sorry.
Yeah. So for nowadays, people who want to do research, they do need to, for example, it's your consideration varies across the stages from you're doing a student and doing early career researcher, and also goes on when you get tenure. So they're very different considerations. I think the question you asked is about the difference between, or and the relation between competence and pragmatism. I think there's a balance to it. Fundamentally, these two concepts are different. As the current understanding of how people do science, or there's a not newish field of science. The current understanding is that we would like to think people who do research, researchers, as having a intrinsic quality as how good they are. We can understand that as competence, and there is other things. For example, performance as of how many papers you produce and things like that. But again, there are definitely more than two things. For example, how external things affect you. I think there are many external things that can affect your career, and you do need to consider that. So you need to consider being pragmatic in a sense, but also keep it to yourself. Try to produce things you value most. For example, high quality research. You need to find different people take different position on these two topics, but I think you need to find your own balance. The reason why people need to be pragmatic is that to survive in the current academia, you need to be able to make a name for yourself and also get money so you can hire more students and things like that. And then you get to produce more papers and do more important research. But you cannot get lost into it and just to chase the fame or chase the money. And instead, you don't really do much of the fundamental field-changing research. So I think it's the question to everybody who do research, that how pragmatic and do so-called pure, like before, like in the earliest sense, how to be a good researcher. Yeah.
Yeah, I was thinking a little bit about sort of like the stereotype of where you might have someone who is excellent at doing some very foundational research, but it basically just doesn't have anything to do with what like the rest of the world cares about. And so the idea is that they might be obviously highly intelligent, but they're not being pragmatic in any sense that, like, for example, they could be applying their mind to a different problem that would be of extreme use to other people. And at the same time, like, I know that there's some people say, sometimes you have to do research for research's sake, just to see where it leads. And they have examples like some studies of, like, I don't know, a zebrafish led to, I don't know, bioluminescent example results that then allowed us to create some new cancer therapy by being able to target and figure out where cells are, things like that. And I probably just conflated like 5 different stories together, but again, it's the idea. It's like people doing something completely random, not completely random. They're doing something in an off-topic field, and they manage to make a great innovation in a related field. But I'm not sure that if those examples are frequent enough to warrant people saying that we're not going to have like pragmatism, like that there should be more of a direction. Do you think that people who are good at being pragmatic are actually more skilled in general as scientists, as in the same skill that makes you able to make pragmatic decisions also helps you make good scientific decisions?
I do think there is a correlation to that, because part of the competence is for you to figure out things that are important, and being pragmatic do help you to do good research. Then, if you can figure that by being more or less pragmatic in your work, you put yourself in a better position to do better research. Then I think if you can do good, you're good at being pragmatic. That shows something about your intrinsic quality and how good you are in doing research.
Yeah, I mean, I tend to agree, and also, the idea is like it's correlated. It doesn't have to perfectly align, but it's hard not to think that the capacity to critically evaluate one's own career is completely unrelated to your ability to critically evaluate and prioritize, which aspects of science you work on. It seems to me that there are prioritization tasks, and that those should be evaluated. If you don't mind, let's talk a little bit about the interplay between math and science. Because you have this quote that says, a good scientific research has three indispensable tasks. You observe the real world phenomena objectively, you construct a formal system that's simple and consistent, and then you map between the physical and the formal systems bijectively. Again, I really like how you insert a mathematical description into this, but it's useful. Can you talk a little bit more about this bijective relationship between the physical systems and the formal systems?
Well, I do use this term bijection intentionally, but I mean, even though it's not necessarily mathematically rigorous, but I think it's useful to think it that way because all the essential characteristics are there. So when I talk about this, is if you do this scientific research, you want to have a theory to it. So there is the real world on one side, and there is a theory on the other side. As for me, how I see scientific study is that you start from observations in the real world, and then you move into some formal version of it, try to discover things, and then the things you discovered should be able to inform you about how the real world works, so you can make predictions and understanding and things like that. So that's how I see every scientific theory should be going. This comes in the relation between math and science. Math, as I see it, is basically a collection of formal science or symbolic systems, and that makes the core of a scientific theory. And it only becomes useful if you make that relate to something that happens in the real world. But on the other hand, the observations you make in the real world needs to have something that is simple and potentially informative to guide your discoveries. So they are close. In this sense, math and science are closely related to each other. One example I can give you is about my PhD research. For my dissertation, I did analyze how drivers behave. Specifically, I studied New York City. I was very fascinated by the iconic yellow cabs. So what I have is some data sets that I can analyze. It's a lot of them, like about 5 years of how all the yellow cabs drive around the city. So I do have the data, which are observations, and then I start thinking. I was asking the question: how drivers decide where to go when they move around in the city during the day. So I can I create a model in my mind how they make decisions, which becomes a formal model, and then that specifically that's a game model or game theoretic model. If you form that, people make decisions, for example, to maximize their income, then there comes a prediction that is called a equilibrium. That prediction, if you have this bijective relation between the math and the real world, everything in the real world should correspond to something in your model, and everything you deduce from that model should have some implication in the real world. So the predictions you get should be able to give it a direction of what you should observe. in your data set. And with that, completes the loop of scientific discovery and how you predict people will behave in the real world.
Hey everyone, we're in the final stretch of our episode, and I'd really appreciate if you could give me feedback on 3 things. First, what was your favorite question of the episode? What did I do right? Secondly, which questions should I have asked that I failed to? And third, what questions did this conversation bring up that you'd like answered in the future? Thanks, and enjoy the rest of the episode. So does this bijective aspect, does this relate to the idea of like the dualism? How do we can we incorporate the idea of dualism more fully in this interface between the math and the science, um, the formal system and the physical system?
Yeah. If you actually, if you check my wiki, there actually are 2 pages. One is called the principle of duality, and the other is more specifically about duality theorems in optimization. So I think you can check the first. It's basically how duality is fundamental in different areas of math, and it's definitely also very related to science, but specifically, I put this nice little diagram that I created. So there is a primer. So basically, there are two things. One thing is called the primal, and the other is called the dual. So these 2 things basically uh, uh, 2 things forms the duality. Mathematically, there is definitely a theory. You can delve into it. It's very formal, but the key idea is basically that everything, as long as you establish a duality or bijection, things that's difficult or may be difficult in one world or in one side can be simple on the other side. So, but because there is a duality connection, everything we discovered in one side has an equal part on the other side. So whenever you can proceed easily, you can map it back to the side where you cannot proceed. So you can always make your progress feasible on one side or the other. So that's the beauty of it.
Yeah, it reminds me of the first place where I was introduced to duals was in linear programming. And the idea is that effectively, and I'll pop up a picture, but the idea is that effectively you could have this very complex linear program on one side, and it would have its optimal point at some vertex. So effectively, people can imagine that like there's this sort of convex space, and you get a convex space defined by linear borders, and um, it'll find its point. But the idea is that no matter how complex it could be, there's actually a dual representation that you could solve equally as well, but would be vastly simpler. Um, well, it's in like easier to read and things like that. And that effectively that the relationship is effectively and it's entirely mathematical. And the idea is that effectively you reverse the objective function and the constraints, and essentially you flip these things on their head, and that if I'm remembering correctly, and that's what creates this duality, and that the amazing bit, like the bit of the magic of mathematics, is that they meet at the same point. Like there's the kicker. It's not just that you can reconstruct this thing in a reliable way, but it's like, oh, and they solve the exact same thing.
Yeah. Well, if you read those things in papers and research, it's hard to get an intuitive picture of it. Not every scientific discovery has a video about it. But yeah, it is duality is a very beautiful thing, and it's really helps in many situations.
Yeah, and I just again on that helpfulness, the thing that caught me about what you're talking about was that if you get stuck in one of these domains, you can try switching to the dual, which is very similar. So effectively, you could take this complex linear program, you switch it to the dual, it becomes simpler, and you can make progress that way. And similarly, in scientific research, there's plenty of times where you need a mathematical abstraction to make progress, where effectively you say like, okay, this is just too complex as it is. I'm going to create a mathematical abstraction. I'll make progress in this domain, see how far I get. And then you switch back into the scientific domain and you start working with that and you create new observations. And then those new observations can help feed into how you need to refine your sort of your more formal representation. So I think it's a very beautiful way, a debugging system, if you will, of logic where you flip between these two things. And I think one of the challenges is for scientific research is, unlike that linear program where there's that sort of perfect mapping where they literally come together like that thing in the Sistine Chapel, that the hands or the fingers touch.
Yeah,
That's what I think of. But in science, it doesn't perfectly map. So it's effectively that sort of inductive element. There's a distribution at the point where the fingers touch, and that's where the adventure is. That's where all that excitement is. So I thought that's a very beautiful way to describe it. Did I miss anything on that concept? Because is there anything else to discuss about that nature of duality?
no, I think it's a pretty good discussion. We'll cover most of it.
Very cool. So let's talk about a bit about falsification. So effectively, you can falsify an argument, for example. And you have a formal logical system, does that change this logical system? So like, how does the falsification interact with these systems? So you have the formal system, you have the sort of the physical system. Does falsification come only via evidence, or does it come via logic, or both?
So scientific discovery, every scientific theory should be falsifiable by evidence, but you hope it is not falsified by evidence. But a scientific theory should never be falsified by logic, because if you think about it, if it can be falsified by logic, it's basically wrong. It's impossible to hold. So if you figure your theory is logically incorrect, then you just give it up and move on to something else. Yeah.
Okay, so just to be clear, when you say cannot be, you mean that if you have a scientific theory and it's already falsified by logic, it should be thrown out. Like that's a sufficient condition to throw out a scientific theory. Whereas, for example, I guess I'm thinking between like necessary and sufficiency. So we have like a logic-based falsification versus a evidence-based falsification. And that if you have a scientific theory that can be falsified just via your line of argumentation, that it can be thrown out right away. Is that at least the first part of what you're saying?
Yeah. It is the case. So in science, for example, in physics, there are many so-called thought experiments. I mean, so the idea is that it's in science, things and theories should be falsified by observations or experiments. But thought experiments is a play on that, saying that, I mean, you just need to think about it, reasoning, arguing by logic, and see if that is correct or not. So if a scientific theory can be is falsified by logic, there is something wrong about it. I'm not saying that you should just throw it away, but because in science it's not exactly math. Oftentimes, if it is logically incorrect, maybe you just go back and reframe your theory, and in that case, that may be a valid theory.
Yeah. So, I mean, I guess one of the problems with like falsification and rejection is that it's a bit too binary to how most scientific research progresses, where it's a non-binary. Essentially, like models are updated, they're corrected, they are revised. Rarely, like technically they're being thrown out in favor of a slightly different model. But I think sort of that continuum in the revision process is a better one. It's not like the heliocentric theory versus geocentric type stuff, where effectively it's like, no, one just really needs to just chuck out the other, but it's more like, okay, we've expanded our boundary. It has a little bit more detail. It's like a more like a we have like our 100th order approximation, and then it goes into the 101st order approximation of what reality is. But yeah, no, I think that is an interesting point. Um, One thing that you talk about is that like scientific concepts, you say, must be measurable unless irreducibly useful. And I was wondering, what is that? What are sort of like irreducibly useful scientific concepts? Are they analogous to like the postulates of mathematics? Um, so, for example, what one of the sort of irreducible assumptions of science that I think that exists are essentially um, the ones that the uniformity of the universe, or effectively that the same physics and the same world and the same scientific process that exists now like continues to exist. I think that's like obviously I can't prove it empirically, but it's an essential assumption similar to like in geometry how a line is the shortest distance between 2 points, and we need some essential assumptions before going ahead.
Yeah. So yeah, you can call those irreducibly useful concepts either postulates or just primitives. Um, so for example, in physics, there is this. I mean, everybody knows energy. It comes very intuitive, and I think people think it should be there. But the term, if you go deep into it, energy, this concept does not exist. Because people think it should be there, and there's attached to it is the called conservation of energy. So essentially, people think there's this quantity that should not change during all kinds of processes, so it should be conserved. Um, and this is useful, and but for example, as physics progresses, we used to have, for example, kinetic energy and thermal energy and all other things. There are different types of energies. Oftentimes, if you look into the history of physics, energy often, whenever the conservation of energy does not hold, people just say there must be another form of energy, and then in the process you maintain the truth of conservation of energy, but you add more content to it. So it's almost, so this is a primitive concept that you're always trying to make it hold because you think it should be correct. Another example is also in physics, it's symmetry. Symmetry is a very important concept, and sometimes it is essential because symmetry simplifies things, and often there are cases when the symmetry is basically a convention instead of a falsifiable truth. So it has a special status in comparison with other statements in physics. For example, the speed of light. If you think about it, um, Einstein has made this observation that the speed of light when it moves away from it and when it moves towards you, it is possible that the speed in the two directions are different, but you cannot falsify it. It is impossible. So by convention, the speed of light is assumed to be the same in both directions. And that is another example where we have to accept that there are things we cannot know.
Yeah, that's a really great example. I was not aware of that one, but again, also intuitively it makes sense. So well done. We're really closing the loop there. Um, so like actually on the topic of closing the loop, so like we've just talked a lot about the interface between mathematics and science, and one of your most recent papers is a very mathematically rich description of a model for Gaussian process subspace regression. um, But the science is there too. It's not just a math paper. The science is there too, and the scientific motivation is rich. The intuition you give is very rich, and frequently many of the problems that I work on, I actually do believe that there's essentially some sort of, I'm going to not describe this well, but you'll get the intuition that there's some sort of like latent manifold that's actually like really kicking things around. And effectively, I would like to find that. And so I guess, how do you bring these ideas to motivate your paper, like the Gaussian process subspace regression paper? Does it make you think about the manifolds bit, the GPs, the model? Obviously, it all fits together, but how do you bring all these ideas together to create a paper like you just did?
Well, I mean, for the GPS paper, honestly, it's a bit of luck, but also it also takes revision and refining how the model actually goes. I don't get it right from the beginning, but I would say when I start, I think this will be a mostly correct idea. So that's why I picked it. Well, I mean, these things ultimately fit together perfectly. So that's a bit of luck. And not every topic you work on ends up with a very beautiful closure like this. But I think it's a bit of both. The reason why I pick, for example, Gaussian process is that Gaussian distributions are simple. They are analytically tractable. Many of the analytical results we find they need this Gaussian distribution assumption. Even though this is you can say it is restrictive, but it is helpful. It is because once you have analytical results, you can further accelerate, for example, your computation. That is really helpful. That like there are many attributes to make a method successful. For example, theoretically solid and computationally tractable, and things like that. They don't necessarily go together, but you need all of them to be successful. If you have a very theoretically solid method, but it takes a long time to actually you run it, then nobody's going to use it. So that makes a bad method as well. These are the factors that comes into how in the process of making a paper, you decide on the methods you use and how they make a complete piece that's gonna work out, and many things like that. For example, when I first pictured my method, that's the prediction I get is really wrong. So I just figured there's something not right about it. But then you see, okay, so for example, in this case, you realize that the Gaussian process, you need to use the correlation structure, which is if you don't use the correlation structure, your predictions will be bad. And then I rederived those theorems and then put that into a simple example, and it worked. It worked much better. So these things also happen in the process of revising the method.
Yeah, I just as a quick thing, because maybe I didn't describe a previous bit well when we're talking about the duality and hopping back and forth. When we talk about, for example, like the analytical tractability, working with the Gaussian process, and that makes certain things analytically tractable because effectively it has this closed form solution for making predictions, which is a non-trivial tool when we're trying to actually make progress. And so, getting back to our previous bit, that by having that bit resolved, simplified in the dual, effectively, it allows you to make progress on other aspects then that might have a higher priority. So effectively, then you can go into like, okay, well, this makes the analytical aspect, then makes the computation easier, and then I can then work on other aspects. Essentially, you can keep tinkering with other things. Now that there's some like analytical tractability going forward. But no, I think that is really interesting, and just for those who are worried that we're just going to allude to this GPS paper, but never actually cover it. Ruda and I will be having a follow-up conversation dedicated specifically to Gaussian processes, manifolds, and the paper that he wrote. And given that he's been so kind as to guide us through these ideas, I'm sure he will be very helpful in guiding us through and getting us up on that learning ramp, because I think that this manifold learning type of work is something that's very promising and conceptually very useful. Sorry, I didn't mean to editorialize for a long time there.
Well, it's all right.
Cool. But yeah, so maybe just to quickly wrap up, we've discussed a lot of things. What is one question that I forgot to ask?
No, I can't really think of any.
Oh, perfect. Well, I am the ideal host. Kudos to me. So I'll move on. In your lifetime, what is that like one AI or scientific achievement that you would like to see completed?
So by this question, you don't mean what I would like to do, but rather what I would like to see.
Yeah, anything open challenge, all comers.
Okay. I mean, let me just. I'll probably just be modest on this. I would like to see how. I mean, a lifetime is short, right? Scientific discovery really takes time. So let me just be modest.
You're a young, strapping individual. You know, you've got some time.
Um,
You might have 100 years if you're lucky, given scientific progress.
well, one thing that is really exciting in the field of science or scientific machine learning is that people are thinking whether we can, in a way, we're trying to revolutionize how we learn things in science. Previously, we have this differential equations, laws guiding that are governing how things move in the physical world. But those things takes years, and still it's hard to make progress on that currently, because we have this trend in using computing power and super powerful computer models for such as neural networks, where we're thinking whether we can actually learn the physics or figure out the laws behind things that we don't already know. And that's a part of it. Learning what is behind things is one thing, but on the other hand, if we can make the sense of it, like giving it a theory to the scientific side of deep learning, and also making it interpretable. That is, I mean, previous discoveries are interpretable in that we have a nice little equations to it, and we know what each terms mean. But in case of neural network, usually you don't have theory. There is no guarantee to it, and there is for say statistical guarantee to it. There is also no interpretability to it. It's very complex. Nobody knows what those numbers mean. So yeah, if that can be done for scientific discovery, I think that it's a real revolution.
Very cool. I think that is a good answer. I am also on a similar vein. Since I work in medical AI, very eager to start seeing AI and machine learning actually bringing up new, like making true physiological discoveries. Beyond just saying, "Oh, we can predict this and that and the other." But so my final question, which I ask everyone, is, what is one topic or question that you would like for the statistical community to debate?
Um, That's a very challenging question. Uh, well, let me just throw one random stuff. This one topic that I'm currently obsessed with is how to learn a dynamical system from data. And but I mean, there is a very like basic understanding in terms of statistics of it. There's not really much. There's no complete statistical theory behind it. I think it's very much in need. The challenge is that we are dealing with very high dimensional data, and it's very high dimensional, and the samples you have is really small. And if so that makes the problem haven't been touched in statistics. If people can put more focus on these type of um, topic, that is like this can be called a operator inference. Instead of learning a function or linear function, you're actually learning an operator. That's this by itself is more complex, but I think there is a great use to it. I think it needs to have a good statistical theory to it.
That is very interesting. If you don't mind me asking, I'll squeeze in one more thing. Would your answer change if I instead of said statistical community, I said scientific community? So, like, what would be a question like the scientific community as a whole to debate?
Oh, that changes the whole thing.
Mm-hmm. I just like your answer, so I just want to figure. It's like, oh, you're here. I'd like. I did want that answer, and I was just curious about this one too. What do you think?
Oh, okay. So for the scientific community in general, let's keep it in the same theme. One thing is, I would like people to clarify what they actually mean by scientific machine learning or physics informed machine learning, because oftentimes, I mean, it sounds nice, but it sounds nice in principle, but it's just so much vagueness to it that everybody uses it has lost its meaning. And if you don't really know what it means when you use it, why do you use it at all? Why don't you just use some other terms that you know what you mean? Yeah, it needs some clarification.
That is very good. And my question for the statistical community is Ruda Zhang, great guy, love talking to him. Who's going to give him tenure? That's what I want. Who's going to rush out and give this guy
That's a
tenure?
good question. Very good question.
Very good question. All right. Well, so it's out there. And so with that, we have Ruda Zhang from Duke University. Thanks again for a great conversation. I look forward to our next one.
Yeah, thanks, Glenn.